All right. So now let's talk about some shaping or forming techniques. But before we do that, I want you to see if you can come up with a method yourself. So see if you can name a ceramic forming or shaping method, so the actual technique, and then a product that you think could be produced by that method and justify that choice. So pause the video, see if you can come up with something for this question, and then we'll come back and I'll give you a list of some of the shaping or forming methods that we'll talk about in this module. Okay, so this is not a comprehensive list by any means, but these are some of the different shaping or forming methods that we're going to talk about. And so just briefly before we start, when I talk about shaping, we mean that we're obtaining the near finished shape of the ceramic part. And so the shape of that part is obviously going to depend, or is obviously going to constrict what type of shaping method we can use. So some will not be good for certain shapes and vice versa. Okay, so the ones that we're going to talk about today are uniaxial dry pressing. So this is something you should be familiar with from the lab. We'll also talk a little bit more about hot and cold isostatic pressing. So this is a bit of a variation on dry pressing. We're also going to talk about slip casting. So this is a pretty traditional technique from the pottery community. We'll also talk about tape casting, which is a way of forming thin films. And we'll also look at extrusion and injection molding, and also talk about some more sort of prototyping techniques as well. Okay, so uniaxial dry pressing. I start with this because it's an easy, quick way to form simple shapes, and this is something that we use in lab to make ceramics as well. So this shows you sort of a commercial uniaxial dry press setup. And so when we talk about uniaxial dry press, the dry part implies that it's a dry powder. Uniaxial means it's in one axis, is where we're applying pressure. Um, and that's the whole process. So this is actually more complicated than the setup that you saw in lab, but mostly what's happening here is we have a powder. It's in a hopper, which allows us to flow powder into the die. So in this case, this is kind of set up on a assembly line. So the powder comes through the hopper. So to do that, it needs to flow freely. And so that's something that all powders don't do. So that's where an additive might come in handy. And it goes in to the punches. So this is the die, the die body, and then the upper and the lower punches of that die. And so it fills that die, goes in, the hopper goes into that, so it preps it, fills it, and then the upper punch and the lower punch are placed such that we have pressure applied, so we have compression. Once that's done, once we have a compressed compact or green part, we want to eject it. And so we want to get it out of the die so that we can center it, and then we can make the next one. And so that's kind of the idea of this process. On the lab side, this is probably the most common way that people make ceramics for sort of lab experiments, because it's quite simple, and you can do it with very simple techniques and equipment. So we have a hydraulic press, and we have our die assembly here, which should look familiar to what you've seen in the lab. So we have sort of the die sleeve, and then the pressing rod and the top rod. So these are equivalent to the upper and lower punches that you saw before. And this is just going to form a very simple pellet shape, whereas the commercial one you saw in the previous can make a slightly more sophisticated shape than this. So very simple shapes, just really used to study the properties of the material. All right, so let's talk about some of the sort of the problems that can happen with this technique. So cracks frequently develop in the sample, and they can do it from one part, they can do it from the actual ejection friction that is there. So imagine that we have the pellet here, and then as we're ejecting it, we're bringing up this bottom punch. So there's going to be friction between the pellet here and the mold wall. And so that drag that is present can cause this cracking here and here on the ends. And so this causes it to crack, and it actually lifts off this top portion in sort of a cap. And so we call it in-capping. And so this is one way that we can get cracking in these pellets. And so the way we can avoid this is by adding lubricants to reduce that drag from the wall. We can add binders. That increases the strength of the overall part. We can minimize rebound. That's basically how much this pellet will expand once it's out of the die wall. And then we can also maintain a hold down pressure. So basically that is this upper punch. We can apply a little bit of force downward to help eliminate this drag as well. On the other end, we can also, so this is very similar. So this is kind of illustrating the rebound problem. So as you get towards the end of the die, there's going to be a natural expansion, right? As the pellet's no longer under the pressure of the die. And so that can actually expand outwards, as you see here, and that can cause these local tensile stresses, and that can result in these cracks as well. And so we want to try to minimize that rebound in the part. All right, so another problem that can develop is the non-uniformity of the powder itself. So we mentioned that we need a free-flowing powder so that the powder will flow out of that hopper in the commercial setup. Well, we also want it to be free-flowing so that when we apply the force, it's allowed to distribute within the die so that we have an even distribution of pressure. So imagine that we had just a big clump of powder in the middle. Well, if that powder doesn't redistribute within this die, then we're going to get differences in pressure from the outside to the interior here, and so that's going to give us a big issue. So we can definitely add lubricants in this way to allow more particle or to have less particle friction and to have it be more free flowing. And so another reason, so again, it can be from filling. So if it's not filled uniformly, or if there's agglomerates. Those are the clumps. If those clumps are hard and can't be moved freely, then that can also create issues as well. And that can give you some of the defects we saw in the earlier lecture. Okay, so another technique I want us to look at, I won't spend a whole lot of time on this, but I will mention that there's quite a few good videos to watch out there on isostatic pressing if you're more interested in this. But this is connected to the uniaxial dry pressing that we just talked about. Only here you notice it says isostatic. So isostatic means that the pressure is being applied from all sides, not just that one axis. And so what happens here is that we have our powder inside of a flexible mold. So this could be something like silicone or something like that, but it's a very flexible mold. It could even be a plastic, a plastic wrap or something. And so that flexible mold is put inside of a fluid. And so that fluid is then pressurized such that that pressure is being applied to along every direction of this pellet. And so the sort of corollary I want you to think about is if you were swimming, if you're going into the ocean, the lower and lower you get into the ocean, the more pressure that the ocean puts on you, right? And it does that from all directions. That's the same thing that here. We're going to basically pressurize that fluid such that it pressurizes the powder very uniformly. So this can be done and give us very high pressures, but also do it and give us very complex shapes in this process, because it's applying the pressure from all directions, not just one direction, which limits the amount of shapes that we can have. So this method can be done cold. So cold isostatic pressing, sometimes referred to as kip or kipping. That's when we do this near room temperature. So that would be equivalent to dry pressing, where we're just using it as a shaping method. But there's also hot isostatic pressing, or HIP, or hipping. And this is where we do the same pressing, but we do it under fairly extreme heat. And this acts to not only shape the powder, but also center it as well. So it's kind of a combined method of shaping and centering. And so we'll talk more about hot isostatic pressing when we get to the centering section next.